We are and can.
All right. So I did lie. I don't actually play kazoo. So
Not anymore. You haven't found it.
um, so my name is Xiong. I think this is the first time I've presented at this conference. Um,
Don't be nervous, Sean. We're friendly.
So I was going to talk today about the peer provider architecture. So this is a new concept that's developing inside libfabric. Actually, if you want to track this sort of development, it's up in the open source. So this is a new type of architecture we're adding into libfabric. I'll kind of walk through what it does and kind of the purpose of it. I'll provide a high-level description, and then the follow-up. I have two follow-up presentations on this that'll go into more details on how it actually works at a lower level. So start with one to look at kind of the libfabric, what we're calling the classic architecture. Um, and in the classic architecture, right, we have the libfabric API, and we have several providers underneath, each targeting different environments. And the goal here is like the application writes to libfabric, and that gives them portability between these different environments. Um, and this is just an example here, right? I'm showing just for providers. There's obviously several additional providers that aren't shown here, and this is focused on really the Linux subsystem. So the application or middleware can be an AI framework, Nickel, 1CCL, HPC framework like NPI. Can talk through libfabric, can pick to use a TCP provider if they don't have a higher speed network. They can go through verbs, for iWarp, Rocky, Infiniband. I'm showing here the EFA provider from Amazon for their NIC, and again, there's others, OmniPath and Cassini. And then we also have a shared memory provider for intranode communication. And really, this works really well for apps, wanting to run in just one environment. They call libfabric. They pick a provider and then they run over that provider. The problem shows up is, what happens if the app really wants to use two different providers? And this is again a very simple example. The app here, it wants to use, say, our verbs provider for scale out to talk to other operating systems. But when it's talking to the nodes, processes in the same operating system, it could get better performance if it actually uses our shared memory provider as just an example. So today, the app really has one choice. They can have to open both providers. And we have some middleware that actually does this, right? It'll open two different providers. And then it can, based on the target address, it either goes through, let's say, the verbs provider if it's remote, or a local address would go through our shared memory provider. And this gives the app, even though there's some two providers being used here, it gives the app some performance benefits. The disadvantage from the app's viewpoint is, they have twice as many objects from libfabric to manage. So when they want to register memory, they have to register it with both providers. They have two endpoints, which isn't a big deal, but the receive buffering is. So they have to put receive buffers on two different endpoints, one with the verbs, one with the shared memory. And they have to check completion queues on both these providers, the shared memory and the verbs provider. And even something like that, where you're checking the completion queues, it may not be optimal to check them alternating, right? It may be more efficient to check shared memory once for every, maybe 10 times more often than the verbs provider, depending on how your traffic is set up. As one alternative to this is you could have tight coupling between these providers, right? And I'm showing here an example, the EFA and the shared memory provider, those actually exist as having a tight coupling today. So the EFA provider, it reuses the shared memory provider's core. It hides the use of the shared memory provider from the app. So the app is just talking to EFA, and EFA will redirect traffic through shared memory when it can. The problem with this approach is it is a higher development cost. So for every provider we want to deal with, we have to have this tight coupling. So we don't have that today with verbs. That exists today with EFA. And if we wanted to have tight coupling, we would have to go to every provider and have tight coupling with the shared memory provider. Okay. But if we move this on to a more theoretical scenario, right? So what if we want to use more than 2 providers, right? The shared memory one's an easy one for people to get, but what if there's more cases here, more providers that need to be involved? In that case, the tight coupling becomes fairly impractical. So as an example here, right, I have an RDMA network I'm using for scale out. Right, this could be Infiniband, it could just be Rocky. I have my shared memory that does my scale up for intranode. Maybe I have a network that provides, accelerations at a rack level, or Intel term for this is kind of a pod level. So maybe I have a separate network that's not just scale out to my thousands of nodes, but only works with my cluster of say 8 to 16 nodes, very closely physically together. I could also have a GPU-based network. So I have maybe 1, 4, 8 GPUs in my system, and I have a network that actually backs the GPUs. And the GPU network may be within an OS. It may be a network that actually expands to other operating systems. And then I could have switches with some sort of in-network compute, right? So, and I may not want to have, like customers don't often want to have all this come from one vendor. They want to be able to pick and choose and say, maybe my switch is not necessarily coming from the same vendor as my NIC. And I need to leverage that sort of acceleration. So in this case, you can envision you have different providers, each focused in each one of these areas. And the question is how do you use this efficiently? So we want to keep these providers as independent as possible, that ease development costs, ease maintenance. We want to make something that makes this easy for providers to adopt. So we want to be able to have these providers work together, but it needs to be easy for the providers to work together. So we don't necessarily need to have this tight coupling of providers. And this creates what we call our peer provider architecture, or we have these peer APIs. And these are APIs, so here, inside libfabric, we have APIs that are really for providers only. And we have that today between, let's say, what we call our libfabric core and a provider. And this allows the provider APIs are discovery mechanisms to see what providers are present, what features does that provider have, so it can report that up to the application. We want to do the kind of the same thing with what we call a peer API, which allows the providers to talk to each other in a way that's an efficient mechanism. And in the future slides, we'll talk about kind of the orchestration. There's different ways to handle the orchestration here. It can be handled by one of the providers, for example, the verbs provider in this case, could actually handle the orchestration and then decide when it talks to shared memory or not. Or we could have another provider that we're calling a link provider that handles this sort of higher level orchestration between these different providers. And one of the keys here is once we've defined this peer API support, again, we have to touch each of these providers. So all the providers have to implement this peer API support. But once they've done that, we can now start swapping the providers in on its left and right. Right? Verbs doesn't have to know it's talking to a shared memory. Verbs just knows it's talking to a peer that provides some sort of acceleration for it. So how are we going to do this? Right, we're going to talking about possibly 4 or 5, maybe 6 different providers, each develop independently. We want to be able to have them coordinate with each other without losing performance. And we want to, the whole goal here is the application should see better performance because it's able to leverage independent providers focused and optimized for the different areas that it's trying to use. I just have a couple more slides on this. So if I go back to the libfabric API, libfabric exposes an object model to the application. Here are different objects we have, endpoint, domain, fabrics, completion queues. If I look at just the endpoint one, when the application allocates an endpoint, they get the structure here kind of shown on the right. So they get this FID, fabric identifier, EP is our endpoint. And this fabric endpoint has basically just function pointers into the providers. So when the application calls FISend, one of our APIs, what they're actually doing is invoking a function pointer that calls send that goes into the provider directly. So what we're looking at doing with this is can we expand the same sort of object model between providers? And that's the approach we took. So our model, We want to define these different objects, and these are defined specifically to share between the providers. Now, at the application level, the application calls send, or they're going to read the completion queue that comes down through the libfabric API. The send goes to an endpoint, receive queue read just goes to a completion queue. And those objects are allocated by what we call the owner provider. So something has to allocate the data structure here for this endpoint that I showed in the previous slide and actually hand it up to the application. So in our terms, we call that the owner because they actually own this object creation and the object lifetime that the application's using. Under that, we have kind of two new types of objects. We have an owner endpoint and a peer endpoint in this case that are kind of shadow or objects to this active endpoint. And what these peer APIs do is it allows this owner endpoint to be shared with a peer, and then the peer provider allocates a peer endpoint to kind of share back with the owner. And so the owner and the peer providers are able to talk back and forth to each other through the APIs defined by these additional objects. So the peer endpoint defines, start a receive operation. The owner endpoint can have, say, get a receive buffer. And the way it would work in this case, right, the peer provider, when it receives a message, can call the owner to say, hey, get me a receive buffer because I need somewhere to put it. Same thing with the completion queue. When the peer provider completes a data transfer, right, it's going to have access to this owner C queue, so it can simply write the completion directly into the owner completion queue. It doesn't have to have its own completion queue here. It's just going to write it to the owner, and the owner is responsible to exposing this data upwards to the application. Again, these are kind of conceptual areas. So Alexia and Jianxin will both have more details on their next talks that go into more information about how the owner and the peer providers work at a much lower level. So I can stop here if people have questions on the architecture. Otherwise, I will turn it over to, I think Alexia is the next talk.
Hello, Alexia.
Okay, can you hear me?
We can.
Wonderful. Okay. So, as Xiong was mentioning, we have this peer provider architecture that can plug two providers together. And one of the huge use cases for that is trying to offload communication through the shared memory provider. So currently we have a shared memory provider, which provides optimized intranode communication, but that currently is just a standalone provider. So in order to use the provider, you would need to make sure that your application is only running on one node, which really limits the use case for the provider itself. So using the peer provider model, we can plug those two providers together in order to allow any provider to offload their intranode communication through the shared memory. So when we're talking about the what this would look like for the app, like Xiong said, using the SHMEM to offload that from the application's point of view, all we would see is still one endpoint, and we would do this management of the resources and decision on which endpoint to go through internally within the provider itself or within the link provider, as I'll explain later. So in order to do that, we need to share a few resources. We need the biggest elements are that we need to share the completion queue for shared memory in order to write back to the application completion queue when operations are done. And then we also need a shared receive context in order for shared memory to get an application posted receive buffer and coordinate that resource control between the owner and the peer, in this case, shared memory. And then also we need some sort of addressing communication so that, if we have 10 peers with the application, half of those are local and will be used with shared memory, and half of those are going to be remote. So some sort of way to coordinate the local and the remote addresses. So there's a few different ways that we can do this. All of them are conceptually or conceptually a little different, but the end goal of them is all the same. They're all just trying to take two providers, one with shared memory, one core provider of some sort, and trying to leverage those resources in order to offload the shared memory. So the difference here is just implementation, and how much work the provider needs to do in order to tightly couple these, or abstracting it. So the first use case is RXM. So RXM would be what we call the owner of these resources. So RXM would be the owner of the CQ, the owner of the shared receive context, and would also handle the coordination between those resources and tell the operation which provider to use. So RXM would own that CQ, own that shared receive context, and insert and queue and all that stuff into those resources, and would tell SHMEM when to send through the local transport. And SHMEM would then, after that import is done and all that setup is done, SHMEM would be able to directly access the resources that RXM owns. So the second use case is a little, again, they're all the same, but is more tightly coupled. So TCP would directly offload those operations to the shared memory. So TCP would then be the one to own it and to decide where to go, and would own the CQ and SRX and import it into SHMEM. And again, SHMEM would just use those resources that TCP owns. The third case is our new use case that would generalize this so that no provider would have to directly allocate all the SHMEM resources and allocate all these, the core provider resources and leverage those. So we would have this abstract link provider who would act as that owner and would import both of the core provider and the shared memory to use both of them as peers. So in this case, the core provider and SHMEM are both peers that are both using an imported completion queue and an imported shared receive context, and will be writing to that shared resources that the link provider owns. And so the link provider would be that owner and would manage the communication between both of the providers. So theoretically, the performance should be the same in all these situations. The differences here just come down to implementation and who is owning those resources. So the benefit of that link provider is that you would generalize this so that no provider would have to explicitly open a SHMEM endpoint and a SHMEM domain and register that memory and insert addresses, right? This would all be abstracted away into that link provider, who would do that resource allocation for them. So as long as the core provider and SHMEM are able to detect when to use the CQ and the shared receive context as a peer, it could be used by the link provider and be able to leverage this shared memory support. So those are the three different use cases. Again, they all use the same API and everything. It just comes down to the structure. So again, in the RXM, you have RXM would own all of the resources, including the AV, who does what or who is where, right? The remote peers or the local peers. And they would also own the shared completion queue and the shared receive context. So they would be the owner of all the resources and would import. I don't know if you can see my mouse, but I'll use it anyway. Import or add the addresses according to the application addresses so that we can report the correct address in the end. And then it would detect where to send the message, whether it would be through verbs in this example or through shared memory. So it would coordinate, figure that out, and then shared memory would then write the completions directly into the shared completion queue that RXM owns and get its receive buffers from the RXM shared receive context. Alternately, you have a slightly tighter coupling here. This is more of what the EFA use cases. If you're familiar with that, they were the first ones to use the shared memory directly within their provider. So here you have TCP owning all the resources. They have the shared completion queue and the shared receive context, as well as those application addresses. And they will insert the addresses into SHMEM using AV user ID. to tell SHMEM what address to actually report in that completion for the application. And it will make that decision when a send call comes in. Am I remote and should I go through TCP, or am I local and I should offload to SHMEM? So the API calls are all going through the TCP resources, and those are just pointed to using those import calls from SHMEM. And this is that abstract level, that link provider, where we have one link provider using both providers as a peer. So again, abstracted away into one layer that owns all the resources and basically just sets up all the function pointers to make sure that the providers are using the link shared completion queue and the link shared receive context. So again, link owns those application peers and inserts those peers into the core and SHMEM provider, both of them being used as a peer. So with both of them, it would use that AV user ID. Even though these in this example are the same, they could be different depending on the order that they're inserted. So we use that AV user ID, we import both of the resources into both providers, and then links makes that decision which provider to use, and both the core provider and SHMEM provider would then write into the imported completion queue and shared receive context. So again, those are just three different examples of how you could use it. Personally, I think the generic link approach is cleaner, and it is less invasive with the providers, because the RXM and TCP examples, even though it's less tightly coupled, where the provider doesn't necessarily have to post the receive buffers on the correct endpoint, so you're sharing those resources, but it's still pretty invasive in terms of the provider itself. You have to manage those resources within the provider. So abstracting that out into a layer is really helpful, and I think a lot cleaner. But again, you're adding a layer to the stack, so there could be trade-offs. But the goal is to make the performance the same in all these cases. So now I'm going to go over the APIs for if anybody wants to use them. So the completion queue is that first piece that we need to share. So we've defined this peer CQ struct, and that struct has these owner ops. And so these owner ops are how the owner tells the peer how it should write entries into the CQ. So step one would be that the owner would allocate its CQ and would define these owner write ops to tell the peer how to write an entry and how to write an error entry into the CQ. So when it opens the peer CQ using the normal FICQ open call, it would pass that peer CQ into the peer's CQ open via the context parameter on that CQ open call, and let the peer know that it's trying to import a peer CQ using the attribute flags FI peer. So that at this point, the peer knows that it will be using a peer CQ, and so whenever it wants to write an entry, it needs to use these owner-defined ops. So whenever we write an entry, we get that function pointer into the owner ops and are able to write that entry. So that's the completion queue, pretty straightforward. The shared receive context is much more complicated since there has to be two sides of communication. So the owner needs to tell the peer how to get entries, and the peer needs to tell the owner how to start and discard unexpected messages. So there's a couple extra steps. So we have a similar peer shared receive context struct that has these operations, these function pointers attached to them, but we have these owner ops and these peer ops. So when the owner initializes its shared receive context, it will initialize only its owner ops. So how it will tell the peer how to get an entry and such. When we import the shared receive context, we use that, again, the same thing as the completion queue. We use that FI shared receive context, passing the peer CQ via the context parameter and letting it know that it's a peer shared receive context through the attribute flags. And then during this initialization, the peer will then be setting the peer ops to let the owner know how to handle unexpected messages. So the owner ops will just simply be how to get a buffer that was posted by the application, and same with the tag, how to queue a message. So that's an incoming unexpected message that they didn't find a match for it, how to queue it up in the unexpected list. and then how to free an entry once we're done with it. The peer ops will just have that start and discard. So this is how the peer will tell, or sorry, the owner will tell the peer, vice versa. The peer will tell the owner how to start a message once it does get a match for that receive, when the application actually posts that matching buffer, or how to discard it on cleanup or something. So I have a little flow here because I find it sometimes confusing to know how these resources are passed around. So in this example, we just have the owner on the left, the peer on the right. So the owner, again, owns that shared receive context and simply has imported it into the peer so that it has those function pointers using that FI-SRX context call. So in that normal case, we would post a receive buffer from the application. And so that would be queued up in the receive list for the owner. If a message comes in on the peer, we need to be able to get that receive buffer. So we call get message and give that receive buffer to the peer to do whatever it wants with it. Once it's done, it could call free entry, give it back to the owner, and the owner can put it back in whatever resource pool it came from. In the unexpected case, we get a message on the peer and we don't have a matching receive buffer for it. So we can call get message, and because there's no entry, we will allocate one from the owner and return enoent. So we say this is not a match, so we can't start it now. So give me whatever, save whatever overhead or context you need in order to process later. So the peer will save that message into a context attribute of that buffer, and then we'll call queue message to queue it back to the shared receive context. When the application actually posts that FI receive, that's when we can actually call that start message, send it back to the peer for processing, and then it will call free entry once it's done. So that's the way we make sure that that entry is able to go back and forth between the owner and peer during the unexpected message processing. So using the shared completion queue and the shared receive context, those are all the building blocks that we need, and the AV user ID that we need in order to share the shared memory provider with another core provider. Again, there's different ways to do it, but as long as your provider has those building blocks with the peer API, it can be used as a peer. So theoretically, when we get this link provider, it can just plug into that architecture and easily offload that shared memory transport. So that's the shared memory part of it, and I'll let Jianxin cover the collective framework. Or I guess I can stop for questions.
Do we have any questions for Alexia at this time? John Byrne has raised his hand. John, what would you like to ask?
So the things I'm wondering about here are things like looking at this generically, much not just in the Shemin point of view. The AV map, address formats, mode compatibility between the peer providers, modes and capabilities between the peer providers. I mean, what are going to be the rules for things like that?
Yeah, that's a good question. Currently, I have it plugged in that tightly coupled model. And so it is the expectation of the owner to be able to support all those modes. So I do think that that's a limitation, and that's not something that we've discussed yet. The MR modes, we have the owner being responsible for that. But I think that it would have to be the owner who's responsible for any missing support and managing, what can I even go through this shared memory offload, or do I need to do the intranode communication through the core provider because shared memory is limiting. The good thing is, though, with the target of the shared memory implementation is that the shared memory provider doesn't actually have a lot of it doesn't need any modes. It has
that one's should be pretty straightforward. The only thing I could see biting you there would be the decision, how it decides that it's a local thing if it doesn't understand the address format or something.
Yeah. So that would be a link provider specific question. In terms of if you're coupling it tightly with the provider, you already know what
Yes.
what address format you use, so it's easily decipherable. We do have helper functions in the common API that are dependent on address format. So I see it plugging more in there where the link provider sees the address format of the core provider, and we have some helper functions that are able to distinguish
Okay.
how that's interpreted with a core provider.
Okay, thank you.
Thank you.
Do we have any other questions for Alexia? Okay, thank you very much. Let's
Thanks.
move on to Jianxin.
Okay, can anybody hear me? Okay.
We can hear you and we can see your presentation, yes.
Okay, that's great. So I'm Jianxin. I've been working with Intel for some time now. Okay. So Xiong and Alexia talk about the peer provider for the overall architecture and one application. And there's another area of the peer provider can be used is some other like functionality offload. And in this, the collective offload is one of such example. So in OFI, we already have the API for collective operations. So it is defined in the header file in the source code. So right now, the OFI collective API has defined the operations that follow in some way the MPI like operations, including barrier, broadcast, all-to-all, or reduce, and etc. But there's some difference. These operations are defined as asynchronous. So you're doing a barrier, you have to explicitly check in for the completion, and the code itself will not block. And for the API, the headers provide some wrapper function definition for application to use. So those wrapper functions actually is just some macros redirecting the core into some predefined operations associated with the endpoint the operation is applied on. So the collective operations have to be operated on some kind of members. So this is the concept called collective groups. In OFI, the collective groups is defined as we call it AV set. So that is a set of addresses that is a part of address vector. So basically, you adding all those destinations into the address vector, and then you can create a collective group from that address vector by passing certain parameters, like what is the starting member in that address vector, and what is the stride, and what is the count of the group. So just like how you create a communicator in the MPI. So for this address vector set, AV set, we can perform some operations like insert, remove, do intersection, and the union and the div. So in order to get the exact group you want. So with this collective group defined, each member of the group needed to join the group explicitly in order to be able to perform collective operations. So this join operations is also using the FI. There's a function called FI join collectives, but that is also just a wrap around the FI join which is the function for the multicast group. So the collective group is just a special case for the multicast group. So underneath using the same way to operation to define the group, but with a special flag we call it FI collective. And the OFI collectives can be defined for each endpoint individually. So it is represented as a structure inside the FID endpoint. So, so in order to implement these collectives for a provider, we can certainly straightforwardly implement the just implemented that collective operations for that specific provider. However, in reality, we could have multiple different collective offload engines available, and we may want to enable multiple providers to utilize those collective offload engines. And so we have this way, how to go to how to efficiently implement those and trying to minimize the overhead of the implementation and trying to reuse the code as much as possible. So the basically in the past we could have two options. The first option is like the fully independent implementation. So every provider has to implement the collective operations for every offload engine it wants to support. So the pro of this approach is there's a good separation between the providers and also between the offload engines. So all the implementations are totally independent. The cons is there's a lot of duplicated efforts. Many of the code actually are quite similar, but because I mean there's no relationship between the providers, and you cannot share any of them. So this is not the ideal approach we want to take. Another option is implementing a set of utility functions for the basic collective functionalities, and using those utility functions in this implementation for this every provider and for those offload collective engines. So this has the pro of reducing some code duplication. However, one big con is that the utility code has to be coded into certain way, assume certain data structure definition. So all the providers has to be follow the same using the same code, same data structure for those common objects like the domains, endpoints. Those has to be using the predefined header, predefined structure for those things. So limiting what kind of provider you can support, because not every provider following the same layout of those data structure. So with the peer provider architecture, so we have a new option. I think that option is actually better. So based on the peer provider architecture, we could implement the one specific provider, just that for collective support only. So we can define some offload, collective offload provider, and it can work with the main provider or the core provider in using the peer provider API. So providing only the collective functionality, and the main provider will do the majority of work of like define the main data structure and doing all those point-to-point communication and all other things OFI provided. And when there's a collective operation needed, it can just using the offload provider to do this work. So this eliminated the need of creating the duplicated queues and the tables for this between these two providers, because the offload provider and the main provider, they using the peer provider API, so they can share the data structure like completion queue, event queue, and some other objects, and so they don't introduce much resource overhead, or I mean runtime overhead, compared with tightly coupled implementing the provider, the collective operations inside the provider itself. This approach has the pro the same way as if we're using the utility code for the collective operations. It is reduced the code duplication, and also it has the good separation between the main provider and the offload provider. Their interface is only using the peer provider API, not other things you may encounter if we're using the utility code approach. The cons of this approach is the workflow between the main provider and the offload provider. They must be coordinated and well defined. However, with some careful design, this can be handled. So this is an overview of the architecturally of how these two providers are organized. So the main provider and the collective provider both will have the same set of objects defined, like a fabric, domain, completion queue, endpoint queue, address vector, endpoint, etc. However, the collective offload provider will have this, for example, the CQ is going to be created as a peer CQ. It will actually using the CQ defined by the main provider, and using the operation, when writing the completion, it will use the method defined by the main provider. Same for the EQ, and same for the address vector. So for those things, the collective provider does not really carry much overhead in terms of resource. It is just sharing the thing from the main provider. There's a additional special case for the endpoint. For endpoint, we have a additional flag called a peer transfer. Basically, what that means is sometimes we want to the collective offload provider can utilize the point-to-point communication mechanism defined by the main provider. So it will, when the endpoint is created, the main provider can pass a peer transfer flag, and providing opportunity for the collective provider to use the main provider for some peer transfer in the future. So the peer transfer, basically the completion is not going to report it back to the main provider. Instead, it is reported to the peer provider with a predefined callback function provided by the collective provider. So here is the workflow, how to create a collective group. So the application will, for example, MPI have a communicator. So when the communicator is created, it want to create a collective group. So it will call the OFI AV set function to create an AV set, and that function call will pass down to the main provider. The main provider will pass that call to the collective offload provider. The collective offload provider really defined how the AV set is implemented. It will refer to the AV, which is a peer AV defined by the main provider. So it will access the AV from the main provider and creating the subset from that and return that AV set directly to the application. Application got the return, I mean, this is asynchronous operation. You see there's no arrow from the communicator calling the AV set to getting the result. This is the asynchronous operation. After getting the result, the application can get the address needed to create a collective group. So then it will, we'll retrieve that. We'll call this set address function call. It will finally get into the collective offload provider, which will return the address that is going to be used for later operation. So when the application before application can actually do the collective operation, it will need to join the collective group. So as the input, application will call FY join collective with the AV set and the collective address previously returned from the AV set operation. And this call will pass to the main provider. The main provider then will maybe do some additional operation internally, but finally it will call the collective offload provider, which will do the real join operation that could offload to the, offload engine. This work will going to be scheduled to the offload engine. And at some point, it will return that result to the application to see if this submission is successful or not. So at some time later, the offload engine will finish this join operation and create this completion. But this completion is going to be written to the event queue, which is also a peer object defined by the main provider. So it will write to the event queue of the main provider, and the application will call EQ read to the main provider. As a result, it can retrieve the multicast group, which is actually the thing you needed to issue the collective operations later. So when the real collective operations need to be done, the application will call, for example, FI barrier, passing the multicast group previously returned as the representation for the collective group. And that call will go to this main provider. The main provider here may also do some processing. For example, it may need to choose which collective offload provider to use in case there are multiple collective offload provider there. Also, the main provider may create a request internally to track some information that's needed for later use. But those are, implementation details. Anyway, it will, in the end, it will go to the collective offload provider to do the real barrier operation. The offload provider will then schedule the offload work for this barrier operation to the offload engine. And at some point, when this is complete, we'll generate a completion that is needed to be discovered by the application. So the completion is returned to the main provider's completion queue because the collective offload provider is, accessing that as a peer object. So the write operation is defined by the main provider. So the compilation goes directly to the compilation queue of the main provider. And the application will do a CQ read and retrieve this result of this collective operation. Some of the collective offload engines may require a set of out-of-band collective operations for bootstrapping. So this can be implemented in the main provider using point-to-point operations. So the main provider can have some software-based very simple collectives, for example, barrier operations that's defined there. And when he and provided these operations to this collective provider through the peer transfer mechanism. So the collective provider, when doing some bootstrapping, it will call this out-of-band collectives, just calling the FI barrier operations. Here, the barrier 2 is a version of the barrier allows us to pass a flag. So with the FI peer transfer flag, it actually goes back to the main provider. The main provider, so recognizing this flag, say, oh, this is something I need to do. It's not something I will go to call the collective provider in turn. The main provider will do it by itself using the peer point-to-point operations. And the compilation will directly goes to the caller, to the collective provider, because when setting up the endpoint, the collective provider already defined this completion method that needed to for the peer transfer setup. And one more step, this point-to-point based collective operations itself can be offloaded to another provider. So here we say maybe called a utility collective provider. So we can implement a utility collective provider to implementing a software-based collectives that itself will call the main provider for point-to-point transfer. So it may sound kind of convoluted or complicated, but if you just if you follow all the flows carefully, it's not that complicated. It just apply the same strategy. So we have 3 providers here, and the main provider is just acting as a multiplexer. I mean, for example, for the FI barrier calls, it can, if the application call FI barrier, it will determine, oh, this is something application calls, and we have an offload engine. It will go to the offload provider. So offload provider will do this work and complete back to the main provider. And however, if the offload provider when doing the bootstrapping, it need to call FI barrier and it will call the main provider, and the main provider recognize this is a peer transfer call from the offload provider. It can call the utility call provider to call the barrier operation defined there. And the utility provider then will using the main provider for the point-to-point communications by passing the FI peer transfer flag there. And the main provider, when completing those point-to-point transfers, will deliver the completion directly to the utility provider because the completion method is already provided by the utility provider. So yeah, this is probably the whole picture of the we have these 3 providers working together in order to support collective operation that also need some bootstrapping collectives. So for conclusion, the peer provider provides a mechanism to implementing some functional providers without duplicating important data structure. So collective offload is just one such functions that fit this model well. As a proof of concept, we have implemented this utility collect provider. So basically you can testing the this workflow without depending on any of the real hardware-based collective offload engines. We have implemented the utility collective and also using the RXM as the main provider or called a co-provider so they can peer together to work together. This proof of concept also enables the other providers, other collective offload providers in the future can leverage this existing point-to-point based collective implementation, just following the workflow described earlier. So in the future, we may put some effort to actually implementing the offload providers for some popular collective offload engine. When that becomes available, the upper layer middleware then can start taking advantage of this OFFLOAD collectives to get some performance benefit. So that concludes my talk. So I'm open to questions.
Great, thank you. Do we have any questions for Jianxin, Alexia, or Xiong?
Yeah, I've got one. So this is a question for both the collective side and the shared memory piece. But when you compose these different peer providers, what is the locking story like for both in the unexpected message case and when you use a utility collective provider for software emulation and then a collective engine at the same time? How does locking work across these different channels?
Yeah, maybe I can say a few words before Alexia and or Xiong jump in. So the locking mechanism, I think that is implied inside those methods exported by the owner. So basically, the owner write, provided write, or maybe you say those get buffer, or maybe all those methods has to be saved to all the other provider to use.
Yeah, and in the shared memory, we can share the domain to know the locking level. That said, there are optimizations and the parts that we're looking into that have to do with that exact question. But if the peer can know the locking model for the owner, then that's what we would inherit.
Okay, so is it so just by using a peer provider, you're somewhat implicitly taking on the highest locking requirement level?
Right.
Okay, got it.
Cool, thank you. Any other questions for our three speakers? I see one from Tim Thompson. Are these composable providers going to be supported in libfabric 2.x as in not libfabric 1?
We're developing these now. So we're not waiting to like a 2.x to have these defined. The open question is whether we're going to have the peer APIs be binary compatible between different releases of libfabric, or if we'll require that the providers have the exact same version of libfabric. And that deals more with if you had a DL provider. So currently we're not maintaining backwards compatibility on the APIs between the peer provider APIs. But a large part of that's because we're still trying to develop the APIs.
Cool. Any follow-up questions? Okay, thank you. Well, I think if there are